Yeah, so recording has started. So in last class, we have started our discussion with this dynamic CMOS logic design. We have discussed like what will be the basic building block of an dynamic CMOS logic circuit, right? Its operation and its difference from the static CMOS logic design. We have also discussed couple of advantages as well as disadvantages, right? So one of the advantage was number of transistors would be lower in case of dynamic CMOS design, whereas it is should be expected to be higher for static CMOS design, right? Like we have implemented like two Boolean functions, this, right? Same Boolean function using dynamic as well as the static CMOS logic design, and we have seen that for dynamic CMOS logic, it takes less number of transistors to implement that. Right. Then we have also discussed the circuit operation. Circuit operation basically deals with here by like or circuit operation can be divided into two segments. One is the pre-charge, next one is the evaluation. This pre-charge is denoted or is done by this PMOS, and it is denoted as this symbol MP, that transistor which is responsible for recharge, and ME is responsible for evaluation phase, and it has been denoted here with small capital M, small e, right? And the operation is quite simple, right? But like unlike static CMOS, here we have also the clocks are also involved. For example, this particular circuit is an inverter, right? But not in static, but this is a dynamic CMOS inverter, right? So here we have seen like when the input is 0, this is off, right? And when the clock is 0, then this output capacitor gets charged. Output capacitor may not be an load capacitor always. It may be the capacitor which is driving. It may be the capacitor coming out from the next stage. And most cases it is the capacitor from the next stage. So during pre-charge, this capacitor charge, right? During evaluation phase, this is on, but depending on whether this transistor pull down network is on, for example, this one is on or off, depending on that, the output will change from 0 to 1 or from 1 to 0, right? So that is called the evaluation phase. Okay. Then we have also couple of discussed number of transistors is n plus 2 here. Dynamic logic is ratioless logic. Here also no static power dissipation. Again, that is we should put an start here, right? Because here we know that practically there will be some static power dissipation, right? Because of the different leakage currents as well as the subthreshold current. Right, and we have also seen that it is expected to have a faster switching if we use dynamic CMOS logic instead of this static CMOS logic. We have also seen, like for one example, for NOR gate, this G, that is the logical effort for two input NOR gate was 5/3 for static CMOS, whereas for dynamic CMOS it is quite low. So have you figured it out? It is whether it is 1/3 or 2/3. If not, then please again think about it. Whether it is going to be 1/3 or 2/3. Okay. Yeah, these are the mostly the thing that we have covered. Then we have also covered like some of the issues. One of the small issue that we have encountered is that what will be the switching threshold. So we have seen the switching threshold would be given by the threshold voltage of this NMOS, right? And that way we can always understand the noise margin would not be equal. So one of the noise margin would be low, right? That is also an issue. Right? Noise margin low would be lower side. Right. So dynamic power dissipation issue compare. Okay, I have also asked you to compare the dynamic power dissipation issue with respect to the static CMOS power design. So yes. So before we proceed, do you have any doubt so far? Whatever we have discussed. Okay. If no, then let us proceed with this. So there are a couple of other issues, right, other than this small logical threshold or the switching threshold. So one of the issue is called the charge leakage issue, right? So charge leakage issue means what? See, in static CMOS logic, if you if you consider this static CMOS, it is like this, right? So say we are considering the inverter case, in the case of inverter, right? Here it is VDD and here it is Vin. See, when it is charging like this, and when it is discharging, it is discharging like this. Means during charging and discharging, it has a connection with the power rails, right? However, see for here, like this voltage can rise to from 0 to 1 only when this clock is 0. That means when only the pre-charge state, this can rise from 0 to 1. If this voltage somehow decrease, if this voltage output voltage somehow decrease, then during this evaluation phase there is no way that you can anyway charge it to again to VDD, right? Once it is discharged means it is discharged, then again it can be charged only during the next recharge phase, means the when the clock equal to 0. When the clock become 1, there is no way that you can charge it, right? So that is one significant difference here. Okay, so what would be the possible ways by which it can discharge? See, one thing is that this capacitor has charged say from 0 to 1. Now what we expect, once the capacitor has been charged, then it will store that. But there will be subthreshold leakage current, right, for this NMOS. Obviously here also there will be subthreshold leakage. So there might be one path, okay, for by which this capacitor can discharge, right? So one path is the subthreshold leakage. If you consider the other way, this is an NMOS. So here definitely we have another reverse bias PN junction. Please try to recall this is an NMOS. So we have here N plus region and this body is P type. So again that and here the voltage is higher compared to this body. So that makes this PN junction diode reverse bias. So there will be also one leakage current, right? So this is one leakage, this is one leakage. So what are the then sources of leakage current? Here number one is the subthreshold current. What will be the number two? Number two is this reverse biased PN junction, right? So this is number one, this is number two, if we have to write it like this, right? Okay. Similarly, you can also argue then there will be leakage current for this PMOS as well. Yes, you are right. So let us see that. So for PMOS also we have a leakage current. So that is number 3, right? For PMOS also there will be a reverse bias PN junction. Yes, that is also you are right. Right? Are you getting my point here? This is reverse bias, this PN junction. So here will be also leakage current. But these two leakage current is somewhere helpful. See, this two leakage current will prevent the charge leakage, right? But these two leakage current number 1 and 2 is some way detrimental for this charge leakage, because once this charge is lost, there is no other way during evaluation phase that you are going to get back that charge, right? So these are the 4 components here also, but the PMOS leakage current is somewhere helpful, but NMOS leakage current is not that way helpful, right? And say you have designed the PMOS and NMOS with such that this number 1 and number 2 dominates, right? Then what will happen? Soon after this has charged to VDD, and when you have gone to this evaluation phase, this capacitor will discharge, means there will be a resultant current from this capacitor towards this ground, right? Anyway, these two currents are flowing, right? If number 1 and number 2 are higher than number 3 and number 4, then there will be a resultant discharging current. Then this capacitor will try to discharge, right? So if you try to represent that phenomenon using here this diagram, so here you can see we have plotted this clock and here this V out. So this clock, let us see that. So here this clock is equal to 0. So clock 0 means pre-charge phase. So pre-charge phase, this capacitor has now fully charged. Say this capacitor has fully charged. Here, right. Now here onwards it enters into the evolution phase. Here it becomes 1. So here it becomes 1. So this, now this transistor is cut off. Now but this is on, and say this is also okay. Let us say this is not 1 but this is 0. Okay, so in an inverter the input you have given 0. So input given 0 means output is expected to be 1, means VDD, right? So what do you expect? Then you expect that the V out will remain at VDD only. But see, as soon as this happens, right, you you make it, you go into this evolution state, means this transistor is on, right? Due to the resultant leakage path, even if this is higher, then this capacitor will start discharging, and this capacitor will say, suppose this capacitor will discharge like this, right? Again here this is pre-charge, right? Again it will charge till VDD. Again here it is like evolution phase. Again it will discharge here like this. Now try to understand what is the issue if you have this discharging path. The issue is this. See, suppose this one is driving and static. Okay, static CMOS. After that, suppose this is driving and static CMOS, right? Then if this voltage is lower than VDD by 2, right? Then what will happen? That means what? The whole logic has been reversed, right? So for this, are you getting my point? What I am trying to say, suppose after that you have an inverter, okay, and this voltage has reduced below VDD by 2. Then what will happen? It will be considered as logic 0. So the output will be getting as logic 1, which is completely opposite. So you will get the complete wrong output from here. Now you may argue, you might then also argue, then it might, why you are considering that it will reach to VDD by, it will reach below this VDD by 2. It can be even somewhat between VDD by 2 and VDD, right? But not less than VDD by 2. Okay, that's fine. But I think you also understand that, remember this part, what is the power dissipation? Power dissipation with input voltage in static CMOS. You recall, this is the threshold voltage, this is the threshold voltage of NMOS, threshold voltage of PMOS, and the current or power dissipation looks something like this, right? So anyway, if this voltage drop, is more than this threshold voltage, then there will be, due to this leakage current, right, there will be a direct path between the static, there will be direct path between this VDD and ground, right? So there will be a leakage current. This is in case of static, right? So in that case, there will be a good amount of power dissipation, which is a static power dissipation. So you lose the advantage of using the static power dissipation, because that is, you are not going to fulfill that. Static power dissipation is nearly equal to 0. So whenever your output is becoming lower than VDD, or at least below VDD minus V threshold, as soon as you will have that issue, right? The issue will become more severe if this drop becomes significantly lower. Means if this drop becomes significantly higher, means higher than VDD by 2, right? Then there is a possibility that the next stage will understand or interpret the logic in an opposite way. Right. So I hope this is understood, like why it is so important that this output voltage should retain its level, right? So now we have to do something to fix this issue. Okay. So what is the probable solution? Okay. So what is the solution for this to stop this charge leakage? First, we have considered what are the leakage, this sources of this leakage, that is subthreshold and reverse bias PN junction. The question is, we have to eliminate this, right? We have to eliminate this. If we can eliminate this, obviously there will be no leakage, no such issue, no such charge leakage issue. But the question is, for a practical MOSFET design, can we really eliminate the subthreshold leakage current? Can we really eliminate the reverse bias PN junction? The answer is no, we cannot. We cannot really eliminate. We can always reduce it, but we cannot eliminate. Then probably what is the other way solution? Other solution would be we have to some way make sure that this voltage always, this node voltage always keeps at VDD, right? So the possible solution would be to make an arrangement something like this. Here we will add a small PMOS. Small PMOS means small with PMOS, okay, and make this as grounded. Okay, so again please try to notice that what I am saying is that width of this PMOS, width of this PMOS is small, because if it is high, then what will happen, right? When suppose this is 1, this is 1, then it has to discharge. Then it has to, this capacitor has to discharge. But if this width is high, then it will, the current or the charging current that it will supply to the CL will also become high, right? Then the total discharging phenomenon will be affected by this. But if you make this width of this PMOS significantly small so that it can just compensate the leakage current, okay, it can just compensate the leakage current, then you can assure that this node voltage will remain at VDD only. Are you getting my point? So if the situation is like this, here you have 0, here you have a 1, and you have connected this, then as this is not on, now in this case as this is not on, so in this case this will ensure that this node voltage will remain at VDD. This transistor which we have added here is called bleeder transistor. Right, so you have understood a very simple thing, right? Why you are using it, right? Now you might also comment here, then like you have grounded this one, right? Like, but if you have grounded, that means what? So that means always there is a path, always there, because this is always on, this is always on, so there is an always path, okay, or there is an always an power dissipation from here to here, right, due to some leakage or this thing, right? So how can we avoid it? Okay, you can always avoid it by putting probably something like this. Now do not ground it, but add an inverter and then use this inverter output to drive this bleeder transistor. So here then what will happen? Only during evaluation, right? Only during, okay, see here, what I am trying to say is that when this is 0, then only then this is 1. When this is 1, this transistor is off, no current is flowing. Only when this here the output is 1, then only it becomes 0, and then only this transistor can supply the leakage, means supply the charge to the CL which is lost due to this leakage.
Sir,
Right?
sir,
Yes.
sir. But here we are making inverter, right? And again we are adding inverter, and for that inverter we add light, and
Right.
for that we'll
So
add
this,
another.
right. So this is
So
one
that,
issue with, right. Yeah, I agree with you. This is one inverter, but it cannot be only inverter. You could have make suppose 2 input, 3 input NAND gate or any other gate, right? Are you getting my
sir,
point?
but
This
won't we
part,
be
this
facing the
part
same
you
issues for
can
the
make it.
secondary?
Sorry.
Sir, won't we be facing the same issues for the secondary inverter, which we are rectifying here?
No, this inverter is an static CMOS inverter.
Okay, sir.
This is an static CMOS inverter. Okay. So it's easy only, right? Right? How can you solve it? So this is one of the solution by which you can do it. Now there is another issue which is called the charge sharing issue. So what do we mean by charge sharing issue? This is also not difficult, easy, very easy. Now let us see this. Say, we are now considering a different gate. Now, okay, please identify what is this gate. What is this logic?
NAND.
Two input NAND. Very good. So it is two input NAND gate. Okay. So here then you should have two inputs A and B, and say for some reason we have kept B equal to 0. Okay, B equal to 0, A is changing from 0 to 1. Right, and please look into the position of A and B. A is above, then I mean A is sitting, this transistor A is sitting above the transistor B, right? Okay, and so that means because transistor A is much more closer to this V out, okay, and this is V out and it is driving the load capacitor CL, okay, fine. Now during charging, fine, during pre-charge, this has charge from, when this has increased from say 0 to 1, okay, and say that we can stop the charge leakage issue by this charge leakage issue that we have just now discussed by using some bleeded transistor, okay, say that. So that way, that charge leakage issue say is not that way significant here. Okay. So now then what we expect? We expect that this output voltage node should always be at VDD, if should always be at VDD, because now we are saying, what we are saying is that input A is changing, B is not changing. So that means this transistor is always off. We are only turning on this transistor. Okay. So during evaluation state, so should I put it like this? During evaluation state, okay, during evaluation state we have given here 1, we have given here 1, and we have given here 1, we have given here 0. So that makes this transistor on, this transistor off, this transistor on, this transistor off. So okay, anyway, VDD, this is now disconnected from VDD, fine. Okay, so can this discharge to ground? Answer is no, because this transistor is off. However, as probably you have noticed, like during our discussion in layout that I have shared one recorded lecture with you now. So there will be some internal node capacitances as well, right? So here we have one capacitor as well. So does we have another capacitor here, right? And say this capacitor initially has completely discharged. So now the voltage across these capacitors are initially 0. Okay, but as soon as you make this or change this input A from 0 to 1, then this transistor is turning turning on, right? And this capacitor, which is charged till VDD, now it says that okay, I don't have a path to discharge to ground, but I do have some friend with which I can share my charge, right? Because here it is completely discharged, so charge was 0, right? So it can probably now discharge, okay, and share some of its charge with this neighboring capacitor, isn't it? It cannot do it with the other internal node capacitor because this transistor is off, but it can do with this, right? Okay, so let's say that let's give some name here. This capacitor is CA and this capacitor is CB. So CB for this, like if it is B is equal to 0, then CB is not coming into the picture. So far only consideration is the CA. Okay. No, and now can you tell me what would be the result here? Will V out will remain at VDD, or will it increase, decrease? What will happen?
Decrease.
Huh? Increase or decrease?
Decrease.
V out will increase.
Sir, V out will decrease.
V out will decrease, right? Because it will share charge, right? So V out will decrease, and the potential across CA will increase. Isn't it? Please do respond, otherwise how do I understand that you are also with me?
Yes, sir.
Okay, right. Now if I ask you, then please tell me, okay, what would be the voltage, resultant voltage across the CL? What would be the resultant voltage across CL? Resultant V out. How do you find it? Suppose for this phenomenon, how do you find it?
Both the capacitors will have same charge.
Both the capacitor will have same charge, exactly. Very good. Okay. And say this capacitor, okay, the CA capacitor is very low, okay, compared to CL. Then can you comment on the potential developed here? Say this is VA. Can you comment on the potential developed across VA?
It will be close to V out.
It would be close to V out. Are you sure? Say how are you saying this?
Sir, CA is pretty low, right? You said.
CA is very low, right?
So if the charge is,
So the charge has to be balanced, right?
yeah,
Okay. So it's basically the charge Q1 should be like means what I'm trying to say is this one. Say that these two charge has to equate, right? So this is like C1 V1, this is C2 V2, right? Or basically say like basically it's a change in charge. Should I make it change in charge? No. Let us write it like this. So it is delta V into the capacitor CL, delta V1 delta V2 into CA, right? So now delta VL would be equal to delta V1 C1 by CA, right? Okay. Now what we are saying, this CL is much higher than this CA. Then can you comment what would be the value of VL? Okay, tell me one thing. If the CA value is lower, right, then suppose the change is here delta V, okay, and here the change is say delta Vx, and here the change is say delta VL. So which one would be higher? If you
delta
compare
VX.
delta Vx and delta VL, which one would be higher?
Delta VX.
Delta Vx would be higher, right? Very good. Because see, this capacitance is lower, right? Ca is lower. So if little bit charge has been shifted, then that will be sufficient to rise the potential across this capacitor to a high degree, right? So the potential change here would be much higher if the Ca is lower. Now my comment is, can this Ca or can this Vx, or okay, what might be the highest voltage of this Vx, or what would be the maximum change in Vx from 0 to till what voltage it can rise, or in other words, can Vx be equal to VDD?
No, I think because before reaching that potential, the transistor will be off.
Yeah, right, because this transistor, okay, like to supply charge any further, there has to be one threshold voltage drop across this transistor, right? So the maximum voltage, we do not know, right now, like what is the value compare, if you compare like Ca and Cl, so what is the ratio of these two, we do not know. So we are assuming the worst case, we are considering that Ca is very small, okay, so that little bit charge transfer can make this voltage very high. Now the question is, what might be the maximum voltage? The maximum voltage here, the maximum Vx would be equal to VDD minus VTH, right? It cannot be more than this, right? Okay, so if the maximum voltage of this Vx is this one, can you then find what is the change in output voltage here? What will be the change in output voltage? Yes, please tell me. Is this like, this is not that way difficult, right?
VDD minus VTH into CA by CL.
Could you please repeat it again?
VDD minus VTH into CA by CL.
VDD minus VTH by CA plus CL
So VDD minus VTH multiplied by CA by CL.
multiplied by CA by multiplied by CA by CL. Yes, you are right. So, could you please tell me how are you, means how are you coming to this number, or how are you coming to this expression?
So
So this
VDD
will be
minus
the
VTH
final
into
voltage, right? Not the delta.
This is not the final voltage. This is will be the change in this V out. The final voltage, if you want to find, then you have, it would be VDD minus of this. Okay, let's see that. Okay, how are you getting to this number? Okay, so what is the then criteria? The criteria is the charge conservation, right? The amount of charge discharged from here would be, that same charge would be collected by this, right? Okay. So here, what is the previous total charge? It is CLVDD, right? Okay. After that, now it has discharged, and we are assuming that it has changed to V out. Okay. What about CA? What about CA? Can you comment on this? The maximum voltage that we have assumed here, we are assuming CA is much smaller, right? This is from the charge conservation. Fine. Okay. From here you can find what is V out. Okay. So what is V out? V out is the final voltage here. So what will be the change in V out? Change in V out would be VDD minus V out. Yes. Can anyone give me this value from here?
So it will be that same expression.
Yeah, it would be the same expression, but there is CL, right? So it would
Yes, sir.
be
I mean
here.
that VDD minus VTH into CA by CL.
Is it so? See, the CL cancels, okay, and you have to take it on this side. It is CA by CL. It is VDD minus VTH, isn't it? Right. Now here it is VDD minus CA by, okay, this VDD minus here, this VDD minus, this become plus CA. So it is CA by CL, VDD minus VTH, right? So your friend, whatever your friend has said, like this expression, so you can also see we are also getting the same expression, right? And the same expression is coming that way, and that is basically the change. That is not the absolute value. Absolute value of this output node voltage is this one, right? So obviously you can see the absolute value, okay, across this capacitor CL has changed significantly, right? And you know that what is the implication of this type of issue, right? If this output node voltage has changed because of leakage or because of charge sharing, right, the impact would be the same, right? So we have to somewhere stop it, okay, but we have to consider the other cases as well, because here we have considered that for this case we have considered CA is pretty small. CA is pretty small, right? Then only we have considered that the total thing is like means little bit discharge, and that way it is getting to fully charged to like maximum voltage VDD minus VT. But then think about the case if some way CL and CA, these two are comparable. If these two are comparable, then what will be the case? Yes, please tell me. Anyone? CA and CL are comparable. Yes, I am waiting for your answer. Is it so hard to tell? If we can tell for when the CA is for pretty small case, then why can't we comment on when this two will be comparable? Okay, when these two will be comparable, then what will be the total phenomenon? Guys, this is you should tell, right? Either you say like we are not able to understand, or you have to give the answer. But if you are like if you do not say anything, how would I understand that you are understanding, you are not understanding? Okay, so I don't have any other option but to ask by name. Okay.
So if let's say CL and CA are equal,
Okay, CL
then
and CA are equal. Very good.
V
Then
out be close to VTH.
could you please
V,
repeat?
then V out will be close to VTH.
Then V out would be close to VTH.
Yes, sir.
Are you sure? If they are equal, then if they are equal, then is it not the amount of charge that it can, like the amount of charge that is coming here, that will also give rise to this Vx by equal amount? No one is saying anything. So what should I understand? Like, should I do it from here again? Okay, let me then do it here. So can I not copy it here from here? Yeah, let me, that it saves some time. Okay. Just let me copy this. Yeah, and then delete couple of. So this is A, this is B, right? Okay, now this has charged to VDD fully, right? This capacitor will discharge and this capacitor will charge, right? Okay, so say the final voltage it has reached from VDD to V out. Okay, final voltage it has reached from VDD to V out. Okay, then what is the charge that has been shifted from here or transferred from here to this capacitor? How do you find it? That would be CL into VDD minus V out, right? Now that charge has been collected by this Ca capacitor only, right? And isn't it? That charge has been collected by this Ca capacitor only. Okay? Okay. Ca. And that will cause a voltage rise. Okay. Now here is the trick. Please comment what would be the voltage rise. Not anyone. What about Arsh, Ranbir, Aryan?
Sir,
Nikhil?
VDD minus VTH.
VDD minus VTH. Okay, okay. Why that VTH term is coming here now? Could you answer to that question?
This transistor must still remain on.
Yeah, even if this Ca is quite means comparable with Cl, can this voltage reduce this that drastically, and can this voltage become so high so that you have to consider that this VTH issue might arise?
So the voltage rise is CL V out by CA.
That voltage range is rise would be, yes, please say it again.
CL into V out by CA.
Ca into V out by Cl.
CL in the numerator and CA in the denominator.
Okay. C. You said Ca in the numerator or denominator?
Denominator.
In the Ca in the denominator, here it is Cl. You are saying, is this what you are saying?
Yes, sir, I guess.
No, I don't understand. Like, why so much confusion here?
It may be such that the V out means the voltage of CL and CA may be equal
Voltage
because
of
CA
Ca
can
and voltage of Ca and Cl would be equal.
CL yes sir, because CA can now store large amount of charge. So means for very large amount of charge only small voltage increase will be there. So the means the transistor A can always remain on until V out means C voltage of CL and CA are equal.
Right. Okay, I think, okay, let us do one thing. Okay, I think you please, digest this one. Okay, digest this one when the Ca is fully high. Okay, let us come back to this second case tomorrow. Okay, because I don't see then point, like we will finish and move forward and right. Okay, so please take some time, digest this part or think about this part again, the first part. Okay, then think about the second part. We will again do the second part, or if required, the first part again tomorrow. Okay, so let us keep it like this. So we'll start from like this part again tomorrow. Okay, so you have understood that there is a charge sharing issue. Okay, then what is the probable solution? Then the solution wise, it is the same solution that we have considered previous time also. Like we have to identify what is the critical node. So how do you identify the critical node? Say you have analyzed the input combinations A and B, okay, and you have found that the change in A is much more often than change B. So that way, you know, this capacitor, this internal node capacitor is going to charge and discharge quite, or going to like this means this transistor is going to be turned on and off quite frequently. So that means the charge sharing issue would be much more prominent because of the CA only, not because of this CB, right? So as soon as you have identified that the CA is the like critical, like this node is the critical node and this is the capacitor that you have to handle, then what you can do, you can use another bleeder transistor, okay, and you can pre-charge it. Okay, so you can use here clock. So here see what you were doing when this you were pre-charge means when it is 0, right? Then this node is also getting charged, right? This node is also getting charged. So if this is charged, then the charge sharing issue does not arise, right? Because if this capacitor is already charged. Right, this is a simple, pretty simple issue by using an this transistor, always on transistor. Right. Now, I think before we end, so let us quickly discuss this part. There are other issues as well. So one of the severe issue is called the cascading issue in case of dynamic CMOS logic. So what do you mean by this this cascading dynamic logic issue? So here you can see the first part. The first part, it is one inverter, right? Dynamic CMOS logic. It is driving another inverter which is also dynamic in dynamic CMOS logic in nature, right? So one inverter driving the other inverter, right? Okay. So that's what means the cascading, right? Now here you try to understand what will be the implication if we do it like this. So let's say the clock is like this and the same clock has been fed for all this, for all the stages. So the clock is common for all stages. So let's say, and the input is like this, this is with respect to time. Okay, the x-axis is time for all of them. So the V input has changed like this. So here I think I have written V input like this. So let me also write V input like this. So V input has changed like this. Okay. Now as a result, please comment how V output will change. Anyone? This should now you should be able to answer this. How V output is going to change? Okay. What would be the value of V out here? This here. What would be the value up till this point?
1.
1, very good. So V output is 1, okay. And as soon as it has you know, this input has changed, but you know, it has still the clock is equal to 0. That means still it is in the pre-charge phase. So only evolution phase, let us say that you know, after some delay. So from here onwards, okay, this output has started falling, right? Because now you have given here input 1, so the output is expected to be 0, fall to 0, right? But fall to 0 means the capacitor which has been charged here, that has to now discharge, right? With that also we have some delay which is associated with this, so that there will be some delay. Right. Okay. Now tell me till what point or what value this output can fall. Till what value this output can fall. Please consider this circuit and then tell me.
VTH.
VTH, right? Because once once it falls below VTH, this transistor become off. So VTH, so it has gone and reached, it has changed it like this. So this is V output 1. Okay. Now this is 0, right? So this is the input for the next stage. This is also inverted. So here the output is expected to be 1. So that means VDD, right? And say there is also one this is the driving another next stage, and say the capacitance is CL. So this CL is initially been charged, right? CL is initially been charged to VDD, right? Okay. Now let's see what is happening to this V output 2. Okay, this V output 2. This is interesting. See here, V input 1, like this is the V output 1. V output 1 is the input for the next stage, right? So for the next stage, okay, once this evolution has started, so that means from here, so what this input is seeing, this input is seeing, means for the next stage it is seeing this is already on, right? This is already on, so this is already 1, so that means it will, okay. Before that, I forgot to told you one thing. What is the initial value here? What is the initial value, or what would be the value of V out till this point? Ranbir,
So please repeat the question.
sorry,
Can you repeat the question, please?
it would be,
Can you repeat the question, please?
okay. So during this time period, okay, what would be the value of V output 2? V output 2 is this one. Are Baba, why to think so much about this?
Sir, it will be 1.
It will be 1, right? Because still see the same clock, right? So this up to till this point, this is the pre-charge phase. So pre-charge phase output always reaches to 1. So the output has always reached to, output has already reached to 1 here. Okay, fine. Now from here onwards the evolution has started, right? Evolution has started. Okay, and this is the input. This input is V output 1. This is the input for the next stage. Okay, so now the next stage is seeing that my input is already 1, right? My input is already 1. So what will happen, this V output 2 will also start falling, right? Because it is seeing that my input is already 1, so I should be at 0 state, my output should be at 0, right? So that this input head will also start falling, right? Okay, how long it can fall? It depends at what point, at what time, okay, this this V output 1 reaches the threshold voltage, because once it reaches the threshold voltage it cannot discharge, and it cannot discharge any further. And what is the logic threshold for this inverter? The logic threshold for this inverter is also VTH, right? So till this V output 1 becoming equal to VTH, or the threshold voltage, this capacitor will keep on discharging through this, because then this transistor is on and it will keep on falling through this, means keep on discharging through this, right? Okay, so say this is the point till which it can discharge, right? After that what will happen? After that it will remain to that voltage only, because this is a dynamic logic, right? So once it has been recharged, means during the pre-charge phase, right? Then during the evolution phase there is no other way by which it can charge back to VDD, right? So that means if you directly cascade 2 stages of dynamic logic, you are going to face this issue again and again, right? That means you have expected the output 1 to be equal to 0, that somewhat you are getting, but you have expected the output 2 to be equal to 1, but see, you are getting output which depends, which might be close to equal to 0, which might be below the logic threshold, or which might be near close to this logic threshold, right? So one take away thing from this discussion is that you cannot directly cascade two dynamic logic like gates like this. You have to do something else in between, okay, or you have to do some change in the design so that you can't prevent these issues. Okay, so I think let us, it's already 1, so let us stop here today. But remember, please do go through this part again, the charge sharing issue. Okay, the charge sharing issue for different criteria. We will again discuss this one tomorrow, and from there onwards we will like this dynamic logic part is almost over. Now we are going to start a new topic, which is probably the again somewhat in the past transistor logic, this type of thing. No, I think this part is not over, right? Because yeah, after that, we cannot cascade it, right? So we have to see then what would be the other way by which we can cascade the dynamic logic. So one of the solution is called the domino logic. So we can use this domino logic to sort out this issue, or we might have to do some little bit change here and there, so that probably the dynamic logic only we can use, but instead of this only using the pull down network, we have to alternately use pull up and pull down network. So first pull down network, then pull up network. Means pull up networks means the P network, here the N network, right? In CMOS, you try to understand, here CMOS you are only using this N network, here you have to use the P network, then again N network, then again P network, like that. Okay, on an alternate fashion you have to use this. So this is called this NP CMOS. Yeah, once we discuss this, then I think our dynamic CMOS logic will be over, and we can start with the past transistor logic. And yeah, there are a couple of small things here and there before we start the low power or VLSI design techniques. Okay, then we have to do BiCMOS logic designs. After that we have the sequential circuits. Okay, then thank you. But please do think about this part, charge sharing issue again. Okay, we will take start our discussion from this point onwards tomorrow.